So this is interrupt-driven I/O. Before, at the end of last lecture, I said that this will be run count minus 1 times, but that was wrong. This will be run count times, okay? This will be run count times, but this one will be run count minus 1 times, okay? Because we printed the first character here, and we will print the rest of the characters count minus 1 with this time, but this procedure will be run count times because the last time I get the interrupt, I will say that I am done with the interrupts. Okay, so this is interrupt-driven I/O. Programmed I/O has some advantages, like it is simple, it is fast in terms of using the printer, but it is inefficient in terms of CPU utilization. Interrupt-driven I/O is more efficient in terms of CPU utilization. Okay. It is better than programmed in terms of CPU utilization, but again, interrupt switching, context switching, and getting the interrupts and everything, it is wasting some CPU time. The solution is to use the DMA. If you use the DMA, you don't have any interrupts. Your CPU doesn't do the I/O. All the I/O is done by the DMA. So you are not wasting any time, CPU time, for the context switching. So the third I/O method is the DMA. Okay, but DMA requires specialized hardware, and that hardware is sometimes very complicated because some DMA controllers can manage more than one DMA for 5-8 DMAs at the same time, so it might be expensive. The DMA controller feeds characters one by one to the printer one at a time without any CPU interrupts. CPU is not doing anything. CPU is doing some other useful stuff. Okay. Actually, DMA and the programmed I/O is very similar. They are very, very similar. Only in DMA, the bytes are transferred by the DMA instead of CPU. So the only difference between the programmed I/O and the DMA I/O is that the algorithm is the same. Instead of CPU, the DMA chip does the byte transfer. Okay. So the big win for the DMA is reducing the number of interrupts from one character to one per buffer printed. Only you get a new interrupt after all the file is being printed. After you print all the file, okay, you get a interrupt so that you know what is happening. So instead of count number of interrupts, you just have one interrupt, which is much more efficient for the CPU. So this is the code for the DMA. So when you from side A so here code executed when the print system call is made. Okay, I copy my buffer to P and I set up my DMA controller and I block. Okay, I am blocked. And in interrupt service procedure, there is only one interrupt happening. That interrupt happens when the whole buffer is printed. Okay, when the whole buffer is printed, I say that okay, I handle this interrupt, I unblock this user, and I return from the interrupt. Okay, so single. This is run only once. Okay, this is run only once, but this is run count times, and each one is very expensive because you do the context switching. This is run only once. In this case, this is run count times, but each one is 10 milliseconds. Each loop iteration here is 10 milliseconds. Okay. In this case, this one is 10 milliseconds. Okay. How much is this? How many milliseconds is this? How many milliseconds is this? Including the interrupt handling, context switching, and everything. It should be much less than 10 milliseconds, otherwise it would be as expensive as the programmed I/O. So this is by itself, this many lines of code is maybe a few nanoseconds. not milliseconds, a few nanoseconds maybe. If you put the context switching and everything, maybe in total this would be maybe 1 millisecond. So you are saving maybe 9 milliseconds. 9 milliseconds for each character, okay? For each character. Let's say if you have 10 characters, this will take 100 milliseconds because 10 times 10 is 100 milliseconds. For this one, it will take each one is going to take 1 millisecond and 1 millisecond here. This one will take total of 11. The first one will take, this one will wait 10 milliseconds and each one will take 1 millisecond, okay? So it will take 11 milliseconds. So from 100 to 11 milliseconds for the CPU. Again, for these are the CPU times, not the read times. But for this one will take maybe 1 nanosecond, and this one will take 1 nanosecond. So it will take maybe, oh no, this is plus 1 millisecond because I need to do the interrupt handling. So this will take total of 1 millisecond. So this is very, very efficient in terms of CPU usage. I am not talking about the printing speed. Printing speed is almost the same for all of them. If you consider the printing speed, the fastest one is this one. Fastest one is this one. If you talk about the printer speed, because this is CPU and this is a very, very tight loop. As soon as the printer is available, you just print it. So you are not wasting any printer time, okay? But the printer time is not that expensive. CPU time is expensive. So if you think about printer speed, this is the fastest. If you have an expensive peripheral, expensive I/O device, or an embedded system, it might be. Maybe it is best to use programmed I/O instead of DMA or the interrupt I/O. Okay, but for the regular cases, for the regular computers, CPU is the most expensive. CPU time is the most expensive. So this will be inefficient in terms of CPU usage, but more efficient in terms of peripheral usage. So the DMA, we already talked about this, and this is the code for the DMA. Okay, so this is all about this is how we do the low level I/O. Okay, using the interrupts or the DMAs or the programmed I/O. On top of this interrupt handlers, we have device drivers, and then we have device independent operating system. Let's look at this interrupt handler software in a little bit more detail. We talk about interrupts in terms of hardware, what the hardware does. The interrupt controller gets the interrupt and it sends that interrupt address to the CPU. CPU starts handling it and it sends back an acknowledgement. And after that, CPU handles, the operating system handles the rest of the interrupt. And this is what happens when you are handling an interrupt in software. Okay, this is not talking about hardware, this is talking about software interrupt handling. Okay, this is the operating system stuff. The previous I talked about hardware stuff. Okay, so as I said before, this is not a course about computer hardware. This is a course about computer operating system. But without knowing enough details about the computer hardware, I cannot write or I cannot analyze or I cannot study operating system software. Okay, so this is what happens when we do the interrupt handling in operating system. First, I save my registers, not already saved by the interrupt hardware. Interrupt hardware only saves very, very important register, like the program counter or the program status word. It depends on the hardware. So rest of the registers, all the accumulators, index registers and stack pointers and everything is saved first. Okay. And I set up my context for the service procedure. By context, I mean that setting up the page tables, TLB buffers, okay, that kind of stuff. Those are very expensive, you know. Sometimes the page tables might be very, very large. So setting up context is important, okay. And I set up my stack for the interrupt service procedure. I need some stack so that my local variables can live in that stack during my interrupt handling. And I say my interrupt controller that okay, I am handling the interrupt right now. If there is a new interrupt, you can start handling it. Okay, you can start handling it. If you don't have any control interrupt controllers, you re-enable the interrupts, because before this procedure begins, hardware disables all the interrupts until I come to this point. If you have an interrupt controller, you just say that okay, I am now handling this interrupt. Then I copy registers from VerState to the process table. Okay, since I am a process now, I am handling the interrupt. Okay, I copy my saved registers from wherever I left, save to the process table, and then I start running my interrupt service procedure. Okay, because remember this is my interrupt service procedure here, this one. Okay, so every time I come back to this code, I need to reload all the registers and everything, because remember this count and P and I, these are my local variables, or these are my variables in this environment. I need to load them again. I need to get them from somewhere. Where are they? They are in my stack, right? Or they are in my registers, I don't know. That's why they need to be loaded. They are loaded from, okay, copy registers from where saved to the process table, from the process table or from the stack, wherever, okay? And I run my interrupt service procedure. After I am done, now what I need to do is choose which process to run next. Because this was an interrupt, I interrupted some process. Next, some process has to be run again. This process might be the same process that I interrupted or some other thing. Okay? So to do that, I need to set up my context again, another context setup. And although I load all of my registers and PSW and everything, and I start running the new process. Okay, so interrupt handling has hardware procedures and software procedures. If you combine them all, it is expensive. You don't want the interrupts to happen a lot, but interrupt saves a lot of interrupt saves our lives when we do the multi-programming, multitasking, because without the interrupts, I cannot interrupt the running process. They are necessary, but if you do it, if you use them, if you overuse them, then you are doing lots of context switches, and that is wasting your CPU time. Okay? Any questions about interrupt handling? So we come to interrupt handling many times. Sometimes we talk about hardware interrupt handling, sometimes we talk about software interrupt handling. Hardware interrupt handling is something related to the computer architecture or microprocessor design, but the software interrupt handling is the task of the operating system. Okay. So let's go back to this picture. Interrupt handlers, very low level. About this interrupt levels, these device drivers or device independent code, they don't know anything about interrupt handling or the I/O programming, because all the low level stuff is done at this layer. Let's talk about this device drivers then. Okay. For all the devices, I have a physical device controller. Okay. For this printer, there is a controller, electronic circuit. For this CD-ROM there is a electronic controller. Okay. For this camera, there is a camera controller. Anybody remembering this? This kind of cameras? They were like this big. Sometimes they were like this big. You need to put them on your shoulder. And you remember those? They used to be like 5 kilos or 6 kilos or something. And the batteries were like this big. So nowadays nobody is using this anymore. Nobody is using camcorder anymore. They are using their cell phones. So in 10-15 years, the world is changing a lot. And in 10-15 years, the world will be changing a lot too. So we will always, in the operating system world, we always talk about there is no new invention. We are always using the invention that was done in the 1960s, right? We always talk about this. And when we talk about operating system again, we put up these kind of pictures and we said that, remember, anybody remember this? Or anybody remember this and anybody remember this? Okay, we will do this all the time because the computer hardware changes all the time, and we are going to make this talk over and over again. But the thing is that the computers are getting the PCs like this one, okay, or desktop PCs. They are getting more and more expensive because nobody is buying them, right? I mean, maybe 5 years ago, almost half the homes in Turkey, they had their desktop computers. They were cheap. You buy them and you use them. But nobody is buying any desktops anymore, right? Because they have their cell phones. So the desktop is dying, laptops are dying. Everybody is using their cell phones. So the computer engineers are going to run into trouble because when you do your development, you cannot use your cell phone. You need a large screen, you need a desktop, you need lots of storage, you need fast computers, you need 16 cores and etc. You need a GPU, large GPU. If nobody buys them, they will be very, very expensive and nobody will make them. So that will make our task more difficult. Nowadays we are kind of lucky. We were much luckier maybe 5 years ago because desktop computers there were many alternatives for the laptops too. But nowadays the number of alternatives that you can buy as a laptop is getting smaller and smaller and they are getting more and more expensive. So I don't know what's going to happen. Maybe you could use your cell phone as a temporary development environment. I mean, you can connect a display to it. You can connect keyboards and etc. But they are not designed for high performance computing, right? They are designed for portability. They are designed for battery usage, that kind of stuff. The computers are designed for high performance computing. I can run this device, maybe not this device, but the device in my office for maybe for a month at 100% CPU utilization. Nothing will happen. It is designed that way. But if you keep using your cell phone at 100% utilization for a day, I don't think that it will survive. I don't think that it will survive. It will get hotter and hotter and it will shut itself, or something will happen to it. So maybe in 10-15 years, the computers, as a computer scientist or computer engineer, it will be more expensive and we will have more difficult time finding development environments. Okay, so each one has their own controller, and in the kernel space, they have their own drivers. These are part of the operating system. CD-ROM driver, camera driver, printer driver, USB driver, mouse driver. How many I/O devices you have to have a driver for it. Okay, these are the part of the operating system, and they run usually in the kernel space. They run in the kernel space, and these are the drivers that are living at this level. They are on top of the interrupt handlers. Usually, these drivers are provided by the makers of this device, okay, I/O device. If you bought a new CD-ROM controller, okay, it comes with its own driver. You load this driver to your operating system, and it starts running with this camera. Again, it starts running with this printer. It starts running, okay. In 1960s and 70s, you didn't have this many I/O devices. You have only your hard disk or printer and etc. Only a few of them. That's why they didn't have separate drivers for each of them. The drivers were compiled and linked into the kernel itself. So the driver was a part of the kernel itself. Nowadays this is not possible because we have we have thousands of different I/O devices. So each device has to be installed. Each device driver has to be installed separated to the operating system, which makes the task of the operating system difficult, because when you have a crash in Windows or Linux or Macintosh, doesn't matter, 95% of the time it is a problem with the device drivers. Okay, it's not Microsoft's fault. It is somebody else's fault. If you use a new USB stick from very cheap USB stick that you buy for 4 or 5 Turkish liras, okay, it has its own driver, right? Sometimes it crashes your operating system. I think I crashed this system using this dongle. This one, I bought this maybe 15 liras, right? Oh, don't do this. So it's very cheap. It's very cheap.
Exactly.
Okay. So but it has some driver in it. Okay. It has some driver in it. I installed it. Sometimes when I remove this port, it crashes the whole operating system because it is running in the kernel mode, right? When you are in the kernel mode, intentionally or unintentionally, you may cause some serious trouble. As a user of the operating system, any program that I can compile and run will not crash this computer because I am in the user mode. I am in the protected mode. But if you write a device driver, and if the operating system lets you install its driver to the system, then it may crash the whole operating system. That's why this Apple computers are more, they crash less often because they don't let many drivers run on their system because they say that only this and this and this can run on my system. So you cannot have any cheap USB dongles like these or the hardware dongles like these to run on a Apple operating system. Okay. So for the device drivers, as I said, each controller needs some device-specific code, and that device-specific code might be very complicated, but it is called device driver. It's called device driver, and we show it like this in the kernel mode. Again, I said this before, sometimes these device drivers are so complicated. Sometimes these controls are so complicated. You might have CPUs in them, okay? You might have many core CPUs, 8 core CPUs in them, okay? For graphics controllers, you know the GPUs are already, they have more than 1,000 graphical processing units in them. So most GPUs are more complicated than your computer itself. You pay maybe $10,000 for a graphics card if it has enough number of GPUs. So if the controller is so complicated, then the driver has to be complicated. Some of the drivers are complete operating systems, okay? They are so complicated, you need to run an operating system on top of the controller. But again, if you are concerned about the architecture of the operating system, I view them as a simple driver. I call it device driver. Okay, and that's the device driver is written by the manufacturer, and it is delivered along the device. Okay. Sometimes some controllers, for example, the USB controllers. Okay, using a USB controller, you can control the hard drives, your mouse, your coffee heater, your scanner, your printer, etc. So some drivers are very complicated, like the USB drivers. But again, since they are very popular and everybody's universally using them, they make the end user's job or the life very easy. You don't need different interfaces, hardware interfaces. All you need to do is just connect your USB device to the computer. Everything is handled by the USB driver. So these kind of USB drivers are complicated, but they make the end user's life a lot easier. Okay. For some systems like this Minix 3, the drivers are not part of the operating system. Okay. We talked about this at the beginning of the semester. They say that device drivers are not reliable, so I will not make them part of the operating system. They will run outside of the operating system. They will run in the user mode. If they run in the user mode, okay, if the device drivers are running in the user mode, that means that my driver will be here. Okay, this is my driver. When it needs to access hardware registers of the controller, you cannot go it directly because now you are in the user mode. You cannot go directly to this controller. All you need to do is go through your operating system. So even to read a single byte of data from your CD-ROM controller, you need to make a system call, which will cause a context switch. So these kind of operating systems are reliable because their drivers are in the user space. Using the drivers, you cannot crash your operating system. but they are very, very inefficient. Their I/O times are so slow. Okay, so it's a trade-off. They are reliable, but they are so inefficient, which might be used for some cases, maybe for some military application, for some health applications, because you don't want your nuclear power computer to crash, operating system to crash, because of a faulty driver. Keep your kernel small, but every time you need some kind of a data from your I/O devices, you need to make a system call even for a single byte of data, which will make it slow, but very, very reliable. Okay. So I talked about this. A major source of system crashes are buggy drivers. Since the drivers are becoming part of the operating system for many operating systems, that's the problem. Okay, so since the drivers are used very often, and there are many I/O devices that I wanted to use, sometimes you need to classify your drivers into different groups. One of the driver types is the block drivers. These block drivers load the data and write the data in blocks, like in 512 bytes or 1 kilobyte blocks. These are CD-ROMs are like that. And sometimes we have drivers for the character drivers, okay, like the keyboard and the mouse. And sometimes, without using any specific driver, you say that, okay, my disk is a block driver, it's using a block driver, so my interface is like this. That will make the task of the operating system a lot easier. I don't need any specific drivers for my disk because I know that it's a block driver. Its interface is designed that way. Okay, so these are the things that I want to say about device drivers. Remember where we are. Let's go back. We talk about low-level input-output, including interrupts, and we talked about device drivers. Let's talk about device-independent operating system software. Okay, so now I am at the top level. I don't care about where my file is. All I do is open my file and read my data, etc. So device-independent software. These are our main functions at this layer. Functions of the device-independent I/O software. We are concerned about buffering. Okay. We are concerned about uniform interfacing. Okay. Because I don't see any difference between the different devices. I say that, okay, everything is uniform for me. Error reporting should be uniform. Allocating and releasing dedicated devices. For example, if I want to use a printer, I need to allocate it. No two processes at the same time can use the same printer. You cannot allow it. One of them can use it at the same time. And providing a device-independent block size. When you have block drivers, that means that you are inputting and outputting your data in blocks, like 512 or 1 kilobyte blocks. If your device is not supporting that kind of standard blocks, then this layer of the software, this layer of the operating system has to do this for you, providing a device-independent block size. Let's look at them one by one. This is uniform interfacing. If you design your drivers this way, even if it's a SATA driver or the USB or the SCSI driver, doesn't matter. If the interface is the same, so the operating system task will be very, very easy. But if the interfaces are different, okay, your SCSI disk driver interface, your USB drive interface, they are all different. I cannot put this one here, or I cannot put this. Of course, it's a logical picture. It's not a physical picture. If you don't have a standard driver interface, so each interface, the driver interface has to develop his own interface, which makes it difficult for the programmer, for the operating system. But if you force the programmer to provide a standard interface, like this one, it will be easier to write drivers. Maybe it will be less efficient because I have to follow these interface rules. But for the operating system, it will be more efficient to, it will be more easy to install new drivers and etc. So this is one issue when we talk about uniform interfaces. It doesn't have to be that way, but uniform interface makes the things easier. Okay. So let me skip this one. Another issue with this layer is the buffering. We talked about buffering. We don't like this kind of buffering situation. Why? Because I don't want to put my data to the user space without buffering it in the kernel mode. We talked about this problem. We said that no buffering can cause problems, like when I'm running in the kernel mode, because all the I/O is done in the kernel mode. There would be some page in and outs, so I need to keep a buffer and do it that way. And this is what I'm doing here. Again, this one and this one is not that different. Let me see. This one and this one is not that different. They are using a buffer, but the buffer is in the user space. The better solution is this one. Keep a buffer at the kernel space first. When the whole thing is ready, okay, you copy your buffer to the user space. This is a better solution. I will not get affected from any page ins and page outs, paging systems or the memory management systems. My memory management will be independent of my input output. Okay. The problem with this one is for some cases when my data is ready here, okay, my data is ready here, and but I cannot copy my data to this user space because maybe the user pages are not in the memory yet. So it has to wait here, right? It has to wait here. But if a new package arrives from my modem, okay, in this case, I will not receive that data because I don't have buffer space available here because I couldn't copy it on time. Okay, I couldn't copy it on time. So the solution is, let's use double buffering. Okay, fill this buffer first. While I am copying this data from this position to the user space, if there is new data coming from the network, I can copy that data to the other buffer. So this is called double buffering. This is called double buffering. Buffering saves us many times with different problems. If you use more than one buffer, it's called double buffering. Again, I am using too much space, memory space to store some data, but it is preventing some bad results that might be caused from the operating system complications. So most of the time we use this kind of technique called double buffering. Double buffering is a solution. They say that, okay, instead of using double buffering, maybe you could use the circular buffers. Circular buffer works this way. You know the circular buffers, right? What you do is, okay, this is my buffer. Okay, maybe do it this way. This is my buffer. It's a circular way. These are my bytes. Okay, so this is the beginning of the buffer. This is the end of the buffer. When you read from this buffer, okay, you read, let's say, this character. You read this character and you put this in the user space and you increment this buffer here, pointer here. So you say that, okay, now I read this character A. Now I am increasing this pointer I am incrementing this pointer to point to the next place. When a new data is available, you put that new data here and you increment your end pointer. So you have pointer 1 and pointer 2. This way, using a single buffer, but a circular buffer, I can behave like it's a double buffer. Okay. The operating system advances the second pointer as it removes the processed data. So operating system is advancing this P1. Hardware advances the second one, the P2, the first pointer. Maybe I should make this, let me do it this way, P1 and P2. The hardware advances the first pointer as new data. When I add a new data, let's say I added this character Z and I incremented my pointer by 1. When the operating system reads that data, reads this data, let's say there's a B, I just increment this pointer to point to this place. So instead of, so I can read and write at the same time to the same buffer. This way I can eliminate most of the need for the double buffers. Buffering is a very important technique used by the operating system. If you don't use the buffers, there will be problems related to paging or related to receiving real-time data from your network and reference line. Okay. So again, buffering is used a lot with the networks too. You have taken this networking class, I'm sure. You know there are many layers in the networks. If you wanted to send a package to some other computer, you ask your operating system to send that package. Operating system buffers it, and the operating system asks the network controller to send that data, and the network controller buffers it again. The same data is buffered on the network itself, and the buffer. So the same data 1, 2, 3, 4, 5, 6, 7 times is buffered 7 times. That's inefficiency. That's loss of memory usage. Okay. Sometimes I cannot avoid this. I have to do this way. Otherwise, there will be problems. Because if I don't use this buffer, I am not sure the kernel will keep that buffer all the time. While the network controller is waiting for the network to be available, if it doesn't keep a buffer itself, the kernel might need that space and it might release that space. We don't know. So it will use its own buffer. Again, own buffer. So too many copies of a packet has to be kept in this case, which makes buffering, although it's useful, which makes buffering less efficient, inefficient than using lots of memory space.
Hocam buffer koyarak bu durumu çözmek ne kadar mantıklı? Yani sizin dediğiniz gibi kanayan yaraya sanki yara bandı bastırmak gibi bir şey oluyor.
Yok, esasında kanayan yarayı güzel şey yapıyor, dibine kadar gidip problemin köküne kadar hiçbir problem çıkarmıyor ama onu yaparken de bayağı bir tıbbi malzeme kullanıyorsun. O kadar malzemeye gerek var mı diye düşünebilirsin ya, içi tırnak yarası falan.
Yani
onun gibi yani çok fazla kaynak kullanılıyor buffer yaparken.
Hem de zamandan yemiş oluyor.
Kopyalama da var tabii, evet. Kopyalama da var. Yani ama onu yapmadığın zaman yani user space'e güvenip kernel space'te iş yapamıyorsun. O user space'te orası, tamam mı? Adam bana şikayet çekebilir. Bu burada deyip sonra datayı oradan kaldırdığı zaman şeyi biliyor musunuz? Overflow attack'lerini biliyor musunuz? Kernel şey yapmıyor. Bazı durumlarda eğer kernel'ın size verdiği yerden daha fazlasını kullanırsanız kernel crash oluyor. Zorluyorsun oraya. Yine user space'ten kaynaklanan bir problem. O kadar çok kullanılan bir teknik ki bu sistemleri hack etmek için, denial of service attack yapmak için. Onun kernel space'i alman lazım ve kontrolü alman lazım. Bunu yapmadığın zaman, kernel space'e güvenmediğin zaman içeri kopyalaman lazım. Kopyaladığın zaman kopyası burada oldu. Aynısı network controller için de var. Yani şuradaki network controller eğer tüm datayı kendisi almazsa o network kontrolünü crash edip tüm network'e aşağı indirebilirsin. Bunların yapılması lazım maalesef. Yani tedbir üzerine koyman lazım. Diğer türlü yani kırmızı ışığa ne gerek var ki yollarda? İnsanlar dikkatli olsa geçseler falan diye düşünebilirsin. Gebze'de güzel çalışıyor. Gebze'de hiç kırmızı ışığa gerek yok bence. Ama kaza olduğu zaman da bazen tüm trafik alt üst oluyor. 5 saat yerden kalkamıyor. Ölümler falan da olabiliyor. Tedbir alınması lazım.
Yani buffer yerine belki communication sağlanıp yani hızı düşürelim ya da sen bekle ben daha bufferların dolu.
İşte o zaman da diğer tarafı çok paging mekanizmasına şey yapman lazım. Karmaşıklaştırman lazım. Paging zaten karmaşık bir şey. Diyeceksin ki ya bu buffer koymadım, buraya bunu bir şekilde idare et. Tamam idare edelim, bu da idare etsin. O zaman paging öyle karmaşık hale geliyor ki verimsiz hale geliyor, paging yapamıyorsun. Herkes buffer'ını bekletmiş bir kenarda. Bu yok, bu olmasın, ben buna paging yapılmasın, ben bunu buffer olarak kullanıyorum falan diyor. Bundan çözüm bu. Okay. So I think that's it for today. Tomorrow we will continue from this point.